Hi there S4, welcome to Mr. Bull's Physics, and this is another instalment of the National 5 course. Today we're going to be talking about heat, specific heat capacity and specific latent heat. Before we get into anything though, subscribe to Mr. Bull's Physics. We've got 81 subscribers, let's make the 100 and we can all celebrate. So if you've not done so, please subscribe, okay? Anyway, that's Mr. Bull's Physics. Let's talk about heat today, okay? Now, Mr. Bill's Physics channel, subscribe. Right, so just in your, wherever you're at, if you're at home, if you're revising, quick lesson starter. First of all, heat is a form of energy. What are the units of heat, okay? And what are the units of temperature? So if you're, wherever you're at right now, pause it, think about that for 2 minutes, and then I'll tell you the answer. Should be joules, capital J, okay, joules. What are the units of temperature? Well, the units of temperature we're going to use is degrees Celsius. In future, probably the end of S4, you're going to be looking at Kelvin. We definitely do not use Fahrenheit though, that's the American system. We don't want to touch Fahrenheit, we just want to use degrees Celsius. So, we're going to be talking about heat today. And what we're going to do, we're going to develop an appreciation of the difference between heat and temperature. And whilst also learning about how materials change state. So by changing state, going from like ice to water to solid, all of these things. And success criteria, how will we know we've done this? You will have a clear understanding of the differences in calculations between objects changing state and changing temperature. Right, so the first things first, specific heat capacity. Now, we've said heat is measured in joules. We need to know that because we're going to use the measurement joules every single time we use these equations. And we also need to know that the temperature scale is in degrees Celsius, so that means when we see a question, we know that it's in degrees Celsius. It's going to be asking you about EH equals C and delta T, which is the equation we're going to come on to, which is here. Okay, this is the equation for heat. EH, you're used to seeing EW, EP, EK for all the different types of energy. No different for heat. It's heat energy, EH. Then we've got equals C. This is this thing called specific heat capacity, measured in this weird thing called joules per kilogram degrees C. Do not worry about remembering that unit. That unit is in your data booklet. So look in your data booklet and you will see that there's lots of specific heat capacities of different materials. But what even is it? This is it here. Specific heat capacity is the heat energy required to heat up 1 kilogram of material by 1 degrees Celsius. Okay? So the heat energy required to heat up 1 kilogram of material by 1 degrees Celsius. Right, so I've actually got a kilogram of copper here. So it's the energy that it would take to raise this 1 kilogram of copper by 1 degree Celsius. That's all it is. Okay? Now, we've then got the mass, and then we've got the change in temperature. Okay? Now this thing here is the delta. That's a fancy Greek symbol, Greek letter, and it just means the change. So if you see that, it's the change in temperature. Change in temperature being, if it's 30 degrees and 10 degrees, starts at 10, rises to 30, there's a change of 20 degrees there. Okay? Right, that's the equation. So water has a specific heat capacity of 4,180 joules per kilogram degrees C. That means I need to put 4,180 joules into 1 kilogram of water to heat it by 1 degree Celsius. That's quite a lot of energy. Okay, that's quite a lot of energy. Now, if you're at home, find a kettle, go downstairs, go into the kitchen, wherever your kettle is. I want you to fill up to 1 kilogram, 1 litre of water, and I want you to guess how long that kettle will take to boil. Okay, now you will know that the kettles do not boil instantly. I wish they did, it would make it such a better experience, but you need to wait for about 2, 3, 4, depending how good your kettle is, minutes until it's boiled. And that's because water has such a high specific heat capacity. It takes so much energy for that water to raise its temperature. So you need to click the button and wait a wee while because it's going to take time for the energy heat up that 1 kilogram of water. Okay, so try that, see how long it takes for your kettle. The ones in school, when I did it with my class, was about 3 minutes, round about there, so it does take a wee while. Alright, so try that, it's a good test. Now, obviously we can't do an experiment when we're online, but I just want to talk very briefly because the questions in the National 5 exams sometimes talk about, about this experiment and how to make it better, or how to improve on that experiment. So what you would need in this experiment is some sort of supply voltage, some sort of joule meter, which measures energy, and you've got a thermometer, and you've got this heating element, and that's in some sort of 1 kilogram material, such as the copper that I just showed you a wee while ago. Now, this is a bigger picture. So we've got supply voltage, supplying the energy. The energy then transfers that to heat energy, which then heats the copper or the aluminium or the steel or whatever we're using in this cotton wool kind of holder, and we've got the thermometer. Okay. Now we're not going to do an experiment, but what's meant to happen is that you're meant to see the change in the temperature. Once you've seen the change in temperature, then you can use that along with the energy you calculate, and along with knowing that this is 1 kilogram mass, to find the specific heat capacity of different metals. Now, on the whole, metals should have a lower heat capacity than water, because think about it, if you heat some sort of metal and you touch it, it's going to get hot very, very, very quickly. Therefore, you have things like rubber handles or plastic handles. Okay? Now, that's a kind of drawing of it there, but I'm not going to go into that because we're not doing the experiment. The 3 things I want you to know, okay, and I might actually come back to that, but the 3 things I want you to know is to improve this experiment, to make it better, and you saw it there, is to ensure the thermometer and heater are fully inside the metal block. Because when we look back at this, okay, let's just very quickly go back, the thermometer and the heater are not fully inside the metal, which means that there's heat escaping and therefore not completely going into the metal. And what happens if the thermometer, because it's slightly raised, is actually experiencing some sort of energy or some sort of heat from another source, or maybe it's quite cool in the classroom, so therefore that's causing it not to rise as much as it should. So make sure that the heater, heat element and the thermometer are fully in the metal. Okay, that's number 1. Number 2 that the SQA might ask you in a National 5 exam would be then not all of the electrical energy measured on the joule meter is actually going into heating the block. Nothing is 100% efficient. So that energy that's coming from that joule meter is trying to put it all into the metal and heat it up, but there's going to be other ways in which that energy is dispelled. It's not perfect. Okay? So that would be number 2, or B. Last one is fully insulate the metal block to ensure that no heat escapes to the surroundings. Okay, that no heat escapes. Why are we saying that? Well, at the moment, when we look back, we'll just go back one more time, you just see that there's cotton wool just kind of surrounding it. We don't have anything on top, we don't have anything secure. There's going to be heat escape no matter what. Okay, so it's not going to be perfect. So we need to make sure that we insulate it in a way that covers it completely. Now, those are 3 ways to improve that experiment. Okay, the PowerPoint's going to be uploaded. Make sure you look at them, know them. That will be asked in a test or an exam. Please know those 3 things to improve this heat capacity experiment. Right, okay. Now, I want to show you this here. This here is the specific heat capacity of the 4 different metals: aluminium, brass, copper, and steel. Now, as I said, you can see look how low these are compared to water. Like almost like, what? This one here is 8 times less than water. It's a lot, or some more significant decrease compared to water. So you see that these different ones here are very low. That means there's not much energy that it requires to raise their temperature up, and it means that it takes quite a quick time to raise the temperature by 1 degree for 1 kilogram of these metals. Okay, now all of these are found in your data booklet, so you will never be asked to memorize any of these in your data booklet in an exam. If it gives you some sort of metal that's temperature has been raised, you need to go into the data booklet and read up about it, and that's what I want you to do. Okay? Right, that's what we've talked about there. So let's do an example. Example says here, how much energy is required to change the temperature of 0.5 kilograms of water from 18 degrees Celsius to 100 degrees Celsius. Okay, so let's do this on the board. And let's see if this works. Yes, it does. And let's do it in black. Right, so let's put the equation in. EH equals CM delta T. Okay? Now, I know the specific heat capacity of water, and that is 4180. Now, I do not expect you to memorize that. That is in your data booklet, so do not worry if you do not memorize 4180. Okay? Look into your data booklet. The mass, what did the mass say? It said 0.5 kilograms, because we're trying to find out how much energy is required. So we don't need to rearrange the equation. We know that the heat energy for raising this temperature is going to be EH equals Cm delta T. For the temperature, it's going from 18 to 100. So 18 to 100, that's just going to be 82 degrees difference there. Okay? Now, what is that? I'm going to quickly get a wee calculator. Okay, again, we would never expect you to do anything without a calculator in physics. Make sure you have one. Please buy a calculator. See if you're watching this and you do not have a calculator, a scientific one, go on Amazon right now and buy it. Okay, buy one for like £10. They're so cheap. Buy one. No excuses. No excuses. Right. 4180 times 0.5 times 82. And I'm getting a large number. I'm getting 171,380 joules. Now, can I just pause that there? Because this here has got too many significant figures. So if I put this as an answer in my exam, I'm getting a mark off because I've done that to a specific. What I need to do is round that number. In fact, what I'm going to do is I'm going to put it into scientific notation. So what I'm going to write is this: 1.7 times 10, okay, 1, 2, 3, 4, to the power of 5 joules, okay? That's what the answer should be, okay? Please remember that. That's a key bit of information. Now, I'm going to pause it there. I'm going to make another video for latent heat, or the change of state, okay? So I've done specific heat capacity, and that's kind of the first one, EH equals Cm delta T, and this here will be the second video of heat. Okay, National 5, thank you so much for listening, bearing with. Again, this PowerPoint will be uploaded. Last thing to say is subscribe, come on, 100 subscribers, okay, let's do it. Guys, have a good day, tune into the next video if you want to learn about change of state.